So finally, for as far as vectors are concerned, I think this is like the pure vector mass. Like for the most part, like we're gonna try to get into like some other topics after this, but tangential and normal components of acceleration. So the normal scalar component and tangential scalar component are these. Pretty much you calculate them using dt of the magnitude of v. You're taking pretty much the derivative of the magnitude of v. And an is equal to square root of the magnitude of the acceleration itself squared minus at squared. Yeah, at squared. So that's usually the order you pretty much, that's how you solve it. That's how you solve it. Basically, you have to find at first and an when you have a problem involved in pretty much, because this relies on it. And acceleration itself can be written as these two components, at times t vector t, plus an times n. And the binomial thing is b equals the cross product of t and n, t cross n. Torsion, I don't think you need that all the time for a course in this, but who knows. Just to see it once or so, I'll show you the calculation moment it. It's not this. This is like technically writing of it, but it's a lot more complicated to solve. There's a formula that's actually usable. But, and again, refresh these two components. But we're not going to do as much calculate. Well, we're going to calculate them a little bit, but not always. You'll see. So write acceleration in the form, in the form acceleration equals att plus ann, shown here, is written here, without finding t and n. So RT, oh wait. So write A in the form A equals ATT plus ANN without finding T and N. So we have the position vector RT equals A cosine TI plus cosine A sine TJ plus BTK. So this is like a very generalized thing with A and B being numbers. So the derivative of this for V is negative A sine Ti plus A cosine Tj plus Bk. And the magnitude of that is, you square this and square that and square that. It's A squared sine squared T plus A squared cosine squared T plus B squared all in the square root. And furthermore, if you simplify that down, you can take out A squared and you have sine squared plus cosine squared, which is equal to 1. So this basically all becomes A squared plus B squared, the square root of A squared plus B squared. At is equal to derivative with respect to T of the magnitude of V, which is equal to 1/2, which is this bringing down, times 0 times A squared plus B squared to the negative 1/2 power from bringing it, taking, this, 1/2 minus 1, the power. But that's regardless, it's 0. So AT equals 0. Because of that 0, you multiply by 0, no matter what the result is, it's going to be 0. And now acceleration is the derivative of v here, the general acceleration vector. So we write negative A cosine T I minus A sine Tj plus 0k. K just becomes 0 at this point because that's a constant. Derivative of a constant is 0. So k is not considered anymore. No, it's A cosine T, it's negative A cosine T because negative A sine T's derivative is just negative A cosine T, and A cosine T's derivative is negative A sine T. So the magnitude of A, because we need that acceleration vector, is going to be the same thing as before. You distribute out A squared and get, it's A squared times 1. Because cosine squared plus sine squared is 1. You really do need to remember that, especially, because that's like one of the secret things to remember, as I showed you before. So it's square root of a squared. Technically, this has to be the absolute value of a. I guess because for this problem, we're considering that. You know that? It's very generalized. No, the square root of a squared, of course, will be absolute value, so I guess. That's how it works. An equals square root of the absolute value of a squared minus at squared, so absolute value of a squared will be a squared no matter what, and minus 0 squared for at is 0. So it's just absolute value of a. Again, that's what an is. So acceleration can be written as 0 times t plus absolute value of a times n. So its absolute value of a of n times n is just your acceleration in that form. And you don't have to find t or n at all. So number 3, very similar, but we're finding it at a specific point at t. This one, t was not an issue, as you can tell. It just became a times n. Little t did not become an issue. In the end, it very much worked out. Yeah, there was no it was a very simple formula. So here we're looking for at t equals 1. So we're finding this t plus 1I plus 2tj plus t squared k, t equals 1. That's the point. Write a in the form, the acceleration form again, just at a specific value of t, which is 1. Yeah. So, velocity is just I plus 2 because t plus 1 and 2t are both going to be, going to be 1 and 2 respectively, and then t squared is going to be 2t. So let's say get velocity. Then magnitude, it becomes 1 squared plus 2 squared plus 2t squared, which is 1 plus 4 plus 4t squared, all under the square root, which is square root of 5 plus 4t squared. Not much you can simplify beyond that. At is the derivative of that. And you actually have a derivative, like that's actually a little bit to solve. You have to worry about, make sure you know how to do. So you drop down to 1/2 and you have 5 plus 4t squared to negative 1/2 power times 1/2, and the derivative of the inside component, chain rule, I'm pretty sure is what some of these comply by. That's what you call it. So it's 5 plus 4t squared, the derivative of that is 8t, so all multiplied together is what you assimilate. So 8t divided by 2 is 4t. And divide by, because we swapped that, we give a negative exponent, divided by square root of 5 plus 4t squared. Then we can solve this for the point t equals 1, because a component in n, you might as well plug it in here. So it's 4 times 1 divided by square root of 5 plus 4 times 1 squared. So it's 4 divided by square root of 5 plus 4, 4 divided by square root of 9, 4 divided by 3. It's simplified 4. Acceleration vector, well, at least this is simple. It's a at t equals 2k. I don't think you can get much more complicated than that. And yeah, 2k. That's what it is now. So because it's v equals I plus 2j plus 2tk, so those will be 0i plus 0j plus 2k. So, and then the magnitude of that acceleration vector is just 0 squared plus 0 squared plus 2 squared divided by technical square root of that. So square root of 4 equals 2. So this means that a of the acceleration vector of 1, magnitude of it, will be equal to 2. Because it's going to be 2 no matter what t is. So an of 1, t equals 1, is equal to square root of a of 1, the absolute value of the magnitude of acceleration vector at 1 squared minus at of 1 squared. And this becomes quite simple from here, I say. 2 squared, the square root of 2 squared minus 4 thirds squared, that's 4 minus 16, 9. We can multiply 4 by 9 over 9 to get 36 minus 16 over 9. 36 over 9 minus 16 over 9, you keep the denominator together. And then it's equal to square root of 20 divided by square root of 9, which is equal to 2 square root of 5 divided by 3. Then the acceleration vector is written as that should be at of t plus an, and was a vector. When you draw these arrows, sometimes you might miss one. Regardless, acceleration at 1 is equal to 4/3 t plus 2 square root of 5/3 over divided by 3n. And that's how you get it. These writing acceleration are not the hardest if you remember the formulas. And now, find RT, N, and B at the given value of T's and find equation. We're going to skip the second part, finding equations, because I don't think you're required to know that for most calculus courses. I feel like it's a little bit extraordinary. You might just, it's more important just to find these values. I'm going to ignore that. So the position vector is cosine t I plus sine t j minus k, t equals pi fourths. So you find that value of t. R of pi fourths. Right. Okay. Still could be minus k, but the other two have to actually plug in. So cosine of pi fourths, sine of pi fourths. These are both going to be square root of 2 over 2 if you remember your unit circle from pre-calc. So that's trigonometry. So that's that. That's one of the four things. So we need to find v in general. V equals negative sine t I plus cosine t j plus 0 k. Okay, and then you get 1. The magnitude is going to be 1 because it's sine and cosine squaring them, whatever, or negative sine and cosine, and adding them. So t is equal just essentially to v in this case. Negative sine ti plus cosine tj. As derivatives worked. So t of pi fourths is equal to negative sine pi fourths I plus cosine pi fourths j. It's going to be again square root of 2 over 2. Like all these sine and cosine things, pi fourths is going to be just different depending on the sign in front of them. So it's negative square root of 2 over 2i plus square root of 2 over 2j. The derivative of t in general is negative cosine ti minus sine tj. And the magnitude is 1. I'm going to end it with calculating b and n. So n is equal to this approach. So it's negative cosine ti minus sine tj. And at pi fourths, it's going to be negative square root of 2 over 2 divided by I minus square root of 2 over 2j. And then b, the fun part. Good thing that k is not involved. T and n don't have 0 as k components, so the cross product's a little bit easier. As you can tell, there's a lot of zeros here when we do it using this method. It's all going to be in terms of k, ironically. And that's if you go geometrically, there's probably some reasoning that if you have just things in I and j, orthogonal have to be in the k direction pretty much. But yeah, the vector b is equal to the cross product of t and n. So in the end, you have negative sine t, negative sine t times alright. Let's see here, it should be negative. Make sure there's not a mistake here. The answer is right. Make sure it's right for the reason. We have negative cosine ti. No, we have to find t. So t is negative sine t plus cosine t. We got the right answer here, but let me see here. That should be negative. Okay, I get it. Okay. So technically this is wrong. It should be, see, negative sine t, negative sine t. That should be, yeah, it's plus negative, so it should be not cosine t. But that's what happens. You can sometimes misread this, depending on, with all this work going on, you can accidentally misread something. So this should be really, it should be sine squared t plus cosine squared t in the end, you know, the k values. So it should be just 1. Regardless, you get the same answer of k. But basically, p of pi force would have always been k. It's basically what I'm reading from here. I would not get too hanged up about it. I guess you get the right answer for pi. No, seriously though. You don't need to do this step. You basically can easily get this to be sine squared t plus cosine squared t, you know, with the individual k values, and you add them together. So it's sine squared t plus cosine squared t, k. Then it becomes just 1. B equals 1 times k. So it's always going to be just k. Even b of pi force would be k. That's what I believe now, looking at this. So ignore that, the little typo here, or linear, when I copied it over. When I did the multiplication, the 6 multiplications. Yeah, because that should be sine, you know, it should be negative sine t times negative sine t, which equals sine t squared. Regardless, I think you get the point. So let's do two more. One that I actually do to be right. Since these are in general, what's this have to work? Now, outside of that side distraction, in 9 and 11, we want to find b and tau for these space curves. And we already know these things from before. If you'll recognize them if you look back on the last video, section 13.4. We have this position function, 3 sine ti plus 3 cosine t j plus 4t k. We did this, so I rewrite what we had, t and nb. We have to find b and tau. In this mess, it's 4/5 and 0k, obviously. 3/5 cosine t, negative 3/5 sine t, negative sine t, negative cosine t. Then you repeat them over here. And you multiply together. In the end, you should get b equals 4/5 cosine ti minus 4/5 sine tj minus 3/5 k. Remember, you combine the terms, you like them. Because that's what you get down here. Yeah. And another thing is sine squared t plus cosine squared t equals 1 is used once more, as I show you this little word. I think you just have to look at this yourself at this point and make sure you understand that. Okay, so this is the formula we have to... Yeah, that's in one notation of derivatives. Dots means the number of derivatives. So we have the first, second, and third derivative for x, y, and z. X, y, and z refer to the components. Oh, okay, we're going to do this for one of them, and that's it. The process. The next one, we're going to skip this and just do b. So r of t is equal to that, so that means that v of t equals 3 cosine t. Yeah, then a of t, because we go through that process and we have to find the v cross a and then do the magnitude of it. I accidentally, yeah. It's v cross a, do one, then we're going to have to do 2 cross products pretty much. This point. And I don't think this is given on tests usually, whenever, you know, because it's like other things are much more needed. It takes a while to do on any serious problem. So we're just going to go over it once. But you do the cross product v cross a. You get these v and a. And eventually you arrive at 12 cosine ti minus 12 sine t j minus 9k. Sine squared of t plus cosine t squared simplifies to 1 times negative 9 is 1. So, yeah, again. Magnitude is you're gonna do the same thing where you get 144 plus 81 because cosine squared plus sine squared is 1. So you get 15, and then v cos a magnitude squared of it is equal to 225. So that's one. This one, I simplified this quickly. I put them as x, I wrote them out here and just did the cos. So luckily, in some of these they get very quick. We have many 0 values, 2 of them 0. So this makes it very easy to do. So you get a lot of, so only 2 of these are serious 2 terms. I wrote all the derivatives. Imagine if, if all these were non-zero, that would be annoying to calculate. Have a low work. So it becomes negative 36 times sine squared t plus cosine squared t equals, negatives. Again, very important. Highlight that every time. That is equal to 1, sine squared plus cosine squared. Of t. Same variable. So negative 36 divided by 225 is equal to negative 4 divided by 20. Negative 4 divided by 25, yeah. That's the never calculate it again. Basically, just understand if you're. I don't think you'll ever have to though. It's just to show more here. Then finally, this one we're gonna finish off. We already got. You should recognize this one potentially. So t and n we have, and they're just an I and j. Oh, so nice. Except for look at these things. Hard to write out. So I wrote them as just x1 and x1, y1, x1. I mean x2, y2. For the cross product showing the work. We have the 0 terms. So it's x1, y2 minus x2, y1 is all we have to worry about. Get our value of for b. The component it's in k and s. So you multiply x1 and y2 and subtract, the product of x2 and y1. So putting this all together, you can tell from above here it's cosine t minus sine t times cosine t minus sine t. Again, we're going to have some very simplification. It's going to simplify like nuts. You can see it here like before. This really does become like a halfway, like a lot of trig terminology used. But it simplifies down, so you get two expressions equal to 1 and other expressions canceling outright, so you have 1 plus 1 over 2, which is equal to 2 over 2, which equals 1, times k, 1k. We have 1k, and that's it for b, so b is equal to k, and that's it. And that's it for this.